Oh, yeah.
Yes, sir.
What's the app recording that you use?
That I use? Record this? Sure. So today we're going to learn all about accelerations. Now an acceleration is a change in velocity, any change at all. When the speed gets faster, we call it a positive acceleration. When the speed gets slower, we call it a negative acceleration. There are people who get confused by this, and they say, no, Paulson, if it's getting faster, that's a positive, that's an acceleration, but if I get slower, that's a... Well, I say it's a negative acceleration, you just read that, but nobody's ever called it anything different?
No, I don't think so.
Yeah, a lot of people say, no, that's a deceleration. Well, the prefix D means negative. So it is saying that it's a negative acceleration, but I like to call it a negative acceleration instead of a deceleration, because if you look for acceleration, you look in a formula for an A, and then people are going to say, no, that's a deceleration, and they're going to look for a D, but that would be bad. You want to find an A, but you just want to make the number negative. So if I slam on the brakes, that really means I was accelerating. And that sounds weird to you, because you think I push on the accelerator to go faster, but your brake is really a negative accelerator.
I got it.
Right? Okay, so if you have a negative number, the negative number needs to be plugged into your calculator that way. Now, later on we will learn about some other accelerations, but for now we can deal with just positive and negative being our acceleration. Now, positive and negative are the direction of my acceleration, so since I have to have a direction in acceleration, then clearly this is a vector term, not a scalar term. Again, scalar terms only have a magnitude or size, and a vector term has both a magnitude and a direction. So this is a vector term. Now, if I'm going to graph an acceleration of a velocity time graph, it would look like this. So this is velocity up the side and time on the bottom. And here I have three cars that are starting off at the same speed, but after a couple hours, are they still going the same speed? No. Who accelerated the most?
Car 3.
The green car, in case you're too far away to read that. The green car has the biggest acceleration. Who had the wussiest acceleration? The yellow car. What is the difference in the graph between those accelerations?
They find the slope.
They all have a different slope. And you find that the one with the biggest slope has the biggest acceleration, and the smallest slope has the smallest acceleration. So you're like, hey, there seems to be a correlation between... You guys are geniuses. So there's a correlation between slope and acceleration. So if I want to find the acceleration, really I just want to find the slope. So this is going to be really easy if you remember how to find slope. If you remember, slope in math class was changing y over changing x. The little deltas mean change. So in our little graph that we had a minute ago, up the side we had speed, and down the bottom we had time. So if our y is on top, and the speed's on top, and the time's on the bottom, well, delta anything is change, and we find change by finding the final minus initial. So if I have a delta V, this is really V final minus V initial. F stands for final, I stands for initial. These are like last names, or first names, and tell them apart, same last name, whichever way you want to look at it. But when we're looking at T, our delta T, we just call it T. We don't call it TF and TI, because when I use a stopwatch, what do you start your stopwatch at? 0. Really? I always start mine at 12.57. Makes it much easier. No, it doesn't. It would make it very hard. I start a stopwatch at 0 all the time, right? So we start at 0, and so my T initial would always be 0, and that's just weirdness. Now, if there are times where you're in the middle of something and then you see what the change in time is, but most of the time when we're dealing with time, we just start off with the t initial of 0. So again, the slope tells me my acceleration, so if slope is this, you guys don't have to write down anything that's not, I'm just showing you where it comes from. White stuff is not as important as yellow stuff. Anyway, you'll get used to it. So the slope is the acceleration. That means to find this, again, delta y over delta x, I have a change in velocity over a change in time. I'm going to end up with this pretty formula. That formula is important. You want to write that thing down. So that is my first acceleration formula. Isn't it pretty? Now again, the V stand for what? Velocity. And VF is velocity. Final, VI is velocity. Initial. Initial means first. Final means last. And T stands for time. Now, some people see it like this. Sometimes you see it written in a textbook in a more linear fashion. And so what happens is we bring the T up. So if T is on the bottom on this side, we bring it to the top on that side, and it's next to the A. So that would look like that. And then textbooks tend to be manufactured in California, and they're weird out there. So they're like, dude, we can't deal with that. It's like negative. It's like God karma or something. So they move the VI over to the other side to make it positive, and it looks like that. But of course, if we left it like that, your math teacher would start foaming at the mouth, because if our unknown is on the right side, life as we know it will end. And so you turn it around the other way, and it ends up looking like that. So you could write it down that way also. Is this a different formula or the same formula algebra differently? Yeah, it's the same formula, just algebra differently. So the same stuff still means the same thing. This is still final velocity, initial velocity, acceleration, and time. So we got it made for that. What happens if I'm looking for time? Those of you who are bad at algebra, this is the trick. The T and the A will just trade places. And so I'll look for T up here, and I'll move A down there, and I've got it made. If I'm looking for VI, again, I and AT are added, so I'd move AT to the other side with a minus, and I'd end up with the minus AT equals VI. So it would look like that. So again, those of you who are horrible at algebra, you may want to write them down all 4 ways. Hopefully you guys get better at it as we're going along, because we'll be doing a lot of that kind of moving formulas around stuff. But again, sometimes you need to look at what the right thing is so you don't make that mistake. Claudia was driving at 14.3 meters per second when she notices the nice officer. 3.27 seconds later, she's driving a respectable 9.71 meters per second. Was her acceleration. Now, to solve word problems correctly, there are a few steps that we want to follow so that we don't freak out. Yesterday we learned about identifying our unit, knowing what our unit was. What we want to do is write down everything that we know. So the first thing we know is 14.3 meters per second. And when we see meters per second, we should think speed or velocity. We like velocity better than speed, so we're going to call it a V. Now, today we learned that there are 2 types of V's. You can have an initial V and you can have a final V. Which one is it, man?
No, it's initial.
Okay, we can tell that it's a velocity for sure just by looking at meters per second. That tells me for sure it's V. To find out whether it's initial or final, we have to actually use English skills. I know it's scary, right? Claudia was driving this speed. Later she is driving this speed. See how the language tells you one was in the past and one's happened later. Okay, so ideally you learned in English class about tenses and stuff like that. And we have to learn that. So 14.3 is clearly our initial velocity. That's the speed that happens before she sees the cop. The cop is what changes everything. So that's before the change, and then later there's going to be an after the change. 3.27 seconds, of course, when we see seconds, we know it's a time, and nobody freaks out over that one. And then our third number we saw was 9.71 meters per second. And again, when we see meters per second, we think velocity. And if we've already figured out the other one's initial, this one must be final. So we got it made. Now what are we looking for? Yeah. So later we'll have to choose between formulas, but for right now we just know this one. So we got it made. We're looking for A. So we're going to look for the version of it that's solving for A. So we got VF minus BI over T. These little parentheses are included in the formula because they're important. So what am I going to put in for VF?
9.71.
Okay, and VI is going to be?
14.3.
And T is going to be?
3.27.
So it's going to look like that. And this is where you should have a calculator. And again, when you plug in, what's the first thing you want to do? Yeah, shove your calculator in the face of people near you and say, "Jata." And you guys can just leave the calculators at your desk. They don't have to be put away. It's very nice of you to do that, but the next class is not to get about it anyway. So again, you want to shove that calculator in the face of someone near you and say, "Da-da-da." And if you didn't, you can correct yourself real quickly. But hopefully everybody at the table gets the same number, which in this case you should have gotten negative 1.4036699725, which we round out to what?
Negative 1. Negative.
Well, again, how many sig figs were here?
3.
And this had? And this had? So this should have? Boy, that was a tough choice, right? So we got negative 1.40, but it's going to be 1.40 what? Again, here we got to figure out what is our unit. Today we learned about acceleration. Before we learned about seconds and we learned about meters per second, but now we're going to have a new unit that goes with acceleration. And how this comes about is it's quite easy. In the formula here, inside the parentheses, we had meters per second minus meters per second, which would give me meters per second. And then I'm going to divide by 3.27, which is in seconds. And if I'm dividing, that seconds is going to be top or bottom? I'm dividing, so it's going to be on the bottom. So then I have two S's next to each other. So that's going to give me meters per second squared. Now, some of you are going to freak out a little bit, and you're going to say, "Hey, Paul, so meters per second squared looks a lot like meters per second." And I'm going to say, "Yeah, but see, this one has a little 2 in it, and this one doesn't." So when you see the little 2 in it, you think, "Ah." And if you don't see the little 2 in it, you think, "Vuh." Okay? So you got to get it stuck in your head. And yeah, they do look alike, but, you know, I have people in class that look alike, and I still have to distinguish between their faces and stuff. So you can do it. So we end up with meters per second squared. Now, our final answer, therefore, is negative 1.40 meters per second squared. But what is the negative there for? Yeah, because most of you, when you see a cop, what do? Yeah, same thing he did. The first thing you do when you see a cop, "Oh, I feel guilty," and you immediately slow down. This drives me crazy when you're driving down the street. Have you ever been driving down the street, like, doing the speed limit, and a cop drives by and everybody slows down?
Yeah.
It's like, he's not going to pull you over for doing the speed limit. You don't have to get slower. Yes?
Can you explain again, why is it meters per second squared?
It's meters per second squared because I took a meters per second, and then I divided by a second, and that gave me an extra S at the bottom.
Oh, okay.
So that's why it comes. So the negative's there because, of course, she was slowing down. So here's a picture of Claudia telling us to try slower. Erica, who's driving at 12.93 meters per second when a cat jumps out in front of her, she slams on the brakes at 19.8 meters per second squared and skids to a stop. How long was she braking? Poor kitty cat. So we see meters per second, we instantly think velocity, but now we have to start thinking, is it initial or final velocity?
Initial.
And again, we have to read, and we say Erica was driving at this when the cat jumps out in front of her. So this was before the cat. The cat is our device that changes everything. So that's going to be my initial velocity. The next number I see is 19.8 meters per second squared. And when I see that little squared, I instantly think
Acceleration.
acceleration. And some people are going, how do they know? We just learned that. So again, when you see the little squared, you think A every single time. You don't see the squared, it's a V. You do see the squared, it's an A. Do we know anything else? What happens is a lot of times in the problem, I will hide a number.
0.
Here, I only showed 2 numbers there, but really there's a third number that's there.
0.
Yes. Because we know she skids to a, so that means the final speed must be 0. So a lot of times, if you think you don't have enough numbers, stop and think. Does it make sense that we are either starting at 0 or stopping at 0? A lot of times that does happen. If you're sitting in a red light and suddenly the light turns green, you know, hey, my initial velocity must be 0. Or if I'm running a race, I know my initial velocity must be 0 unless I'm cheating, right? So that kind of stuff happens and they kind of built into the thing. But one of these numbers is wrong.
Is it acceleration?
Why?
Because it's not negative.
Very good. He noticed that she was braking, and if I brake, that should be what kind of acceleration? A negative one. So if it's negative, then that means I got to go back here and stick a little negative next to my A. Sometimes I give you that as a negative number. Sometimes I'm just plain mean, and I want to figure out, can you figure it out by the wording that that should be negative? Because it's not always given to you that way. So you got to watch me because I'm tricky, man. So we're going to use this same formula, but this time we're looking for
Time.
how long was she braking? How long could be a distance, but clearly here it's a time. So, yeah, if we're going to algebra for t, then of course the t and the a are just going to trade places. And so we would end up with a formula that looks like that. And of course, once we've identified our variables already, all we got to do is shove in the numbers. And again, if you use parentheses here, that'll keep that a negative number, which will cancel out that negative, which will give us a positive time, which is always good. Because if you have negative time, you're in Hollywood, where time goes backwards quite freely, but in real life, we don't see that happen too often. Like, never. I'm not saying it hasn't happened, I'm saying I've never seen it.
Unless you cross time zones.
Yeah.
So how many sig figs are there?
Yeah, one time I was in an airplane and we took a really short flight and I landed half an hour before I took off.
Change time zones.
Because we changed time zones there, yeah. Pretty freaky, man. Okay, by now most of you have stuck your calculator in your neighbor's face and you got? I got 0.6530303030303030303030 ad nauseam ad infinitum. But we would round that off to This one has 4. This one has 3. This one has. This one has.
0.
How many sig figs are in 0?
0.
Unlimited.
Unlimited.
When you're stopped, you're pretty sure you're stopped, right?
Yeah.
Most of the time you bet your life on it. The only time that you don't bet your life on it, have you ever been stopped and you like look at the seat next to you in the car that's just kind of in your peripheral vision starts moving forward and you think you're moving backwards and you're like slam on the brake even though it's on? Has anybody done this? Okay, some of you are looking at me like I'm weird, but it's a really freaky feeling because you swear you're moving and you're okay. Anyway, so it's gonna be 0.653 seconds. Super easy, right?
Well, it's negative.
It's a positive time because 0 minus 12 is negative 12, and then negative 12 divided by negative 19 gives me a positive time. Yes, sir.
There's infinite amount of sig figs, let's say that, for all. So where do you?
If there were infinite sig figs, then we could have infinite numbers, but that's never going to happen. It's just nothing. Nobody has any other questions? You're not worried about the cat?
Did he survive?
The cat survived.
Oh, he has 2 different eye colors.
So we get our bonus picture of the day here.
Yeah.
He has blue lightning plus green eye.
This is a cat that lived at the house that I stayed at when I went to Prince Edward Island with my wife 10 years ago. Her name was Marilyn Monroe. Now, outside of the freaky eye thing going on with Marilyn here,
I love that.
yeah, it is pretty cool. You don't see that too often. But, interesting trivia, for those of you who like trivia, correct? If you see an all-white cat that has blue eyes, what is always true about that cat?
It's a white. It's a male. Female.
His parents had green eye.
It's
It's deaf. If you have an all-white cat with blue eyes, they're always deaf. It's weird. I don't know why. I just know it's true.
Is that cat?
Every all-white cat with blue eyes I've ever met is deaf. Marilyn was deaf.
Half deaf.
No, she was all deaf. And just half deaf. I understand that. I'm telling you, it was a deaf cat, okay?
How do you know?
How do you know they're deaf though?
Well,
You said
okay.
behind him and you said when.
Here's a really good test. Stick a vacuum cleaner right next to your cat and turn it on. What happens to a cat that has hearing? They spaz out and run away, right? A deaf cat is like, oh, what's that? And they look at it. She actually likes to be vacuumed. So, anyway, for homework, of course, you want to do problems B. So on your homework page, you have problems B, and that's a whole 7 problems. And I'm giving you lots of time today to work on this, so you actually get a half an hour of practice time, because I know the process is new, and I want to get it in your head before you walk out of here. So that's where we is.